Good morning to everybody. I'm Marco Simoncelli from Polytechnic of Milano, and I would like to talk with you about seismic performance of moment-resistant steel frames via the incremental dynamic analysis. This work was done with Claudio Bernuzzi and Davide Rodigari, my colleague from the same university. We know that steel frames are the best frames able to resist to earthquake because of the capacity of the material to create, to go into plastic range, to dissipate energy. But there are some cases in the literature in which steel frames didn't respond to the seismic action adequately. One case, for example, is the Northridge earthquake. With the Northridge earthquake, a great amount of connection suffered damage and local collapse. The problem is also nowadays that the damage in the connection is not treated as deep as the problem of the other members. So we need a procedure that is able to understand the develop of the damage in the connection during the earthquake, and which give us an idea of what is the situation of our steel frames after the earthquake. So for this reason, I introduce with this presentation, I introduce two concepts, that is damage estimation and residual load carrying capacity. The procedure herein presented is based on the incremental dynamic analysis. The incremental dynamic analysis is a well-known procedure developed like 20 years ago and is based on time history analysis. So on the base there is the running of several time history analyses with different signal, with different accelerations, by increasing each acceleration from a scale factor of from 0.1 to infinite, theoretically. So, if you look this flow chart, we started with these 44 earthquakes, and for each earthquake we increased the factor from 0.1 to 8 as maximum, until the collapse of the frame. Collapse means instability of the frames evaluated when the convergence of the analysis is not reached, because the frame into the software was modeled with plasticity in members, plasticity in joints. The new concept associated with the incremental dynamic analysis is the estimation of the residual drift, so not only the transient drift, the damage in the joints and in the elements, and the concept of the residual load carrying capacity. This is the frame that was considered, 3 base and 3 floor frames, steel frames, and 4 cases were considered, 2 cases with quite flexible joints, and 2 cases with very strong joints, to see the differences between these two extreme situations. All the models were developed into the OpenSees software with second order effects, and all the joints and the nonlinear behavior was calibrated with experimental test. So we started with the experimental test of Balio cyclic test, and we calibrated the Krawinkler-Ibarra model for the members and the pinching form models for the joints, especially the joints, the flexible joints. You can see here the very good agreement with experimental and numerical reproduction of the cyclic behavior of these elements. For the damage estimation, the low cycle fatigue theory have been used. So the minor rules combined with the rain flow method, have been used to understand the accumulation of the damage cycle by cycle into the joints and elements. When the final value of damage is 0, means no damage. When it is 1, means full damage, so collapse of the element due to damage. This is the low cycle fatigue theory. Some results. With the application of all of these analyses, so great number of analyses, we use the median values to understand the behavior. First results is the representation of the transient and residual drift. We saw a very good agreement between the residual drift obtained numerically and the one estimated with the FEMA code. Another result that we can obtain for this procedure is the fragility curves. That is a very commonly curve used in the research. For example, for this frame, you can see that by looking at an acceleration, the flexible frames with the flexible joints have a bigger probability of collapse with respect to the more stiffer ones. The very important results is this one, that are the residual load carrying capacity. How is estimated the residual load carrying capacity? We performed a incremental nonlinear analysis before the earthquake, and we evaluate the maximum vertical load that brings to collapse. That is the load carrying capacity of the frame. After each earthquake of the incremental dynamic procedure, we ran it again this nonlinear analysis with the vertical forces. So we have the situation of the load with the undamaged frame, and we have the situation of the vertical load with the frame after the earthquake. The ratio between these two situations gives us the residual load carrying capacity. You can see, for example, these curves give us an idea with the acceleration, increasing of the acceleration, what is the residual load carrying capacity. Here is plotted the reciprocal, so when it is 1, we have no residual load carrying capacity. You can see, for example, if we look at DCM frame, from 0 to 1.6 of acceleration, we have 0.25. By increasing the acceleration, we can go to 3 of acceleration, and we don't have any residual load carrying capacity. That means if DCM frame is subjected to an acceleration that is like, for example, in the middle, like 2, have a very big reduction of load carrying capacity, 2 times reduction of the load carrying capacity. We can also relate the load carrying capacity with the residual and with the transient drift. So it's really interesting to see how, by knowing the drift, we can know also what is the residual load carrying capacity of the frame. Another result is the one related to the damage, and you can see the curve related to damage in joints and members, by also related the acceleration to the damage index. If we look, for example, on the interstory drift, how are defined these limits? First of all, how are defined these limits? They are the classical limits that you can find in the FEMA code. The black one is the occupancy. Then we have the life safety. Then we have the collapse prevention. And they are associated to a specific transient drift. So we have the transient drift that give us the limit. then we can relate the other parameters, the residual drift, the residual load carrying capacity, and the damage. For example, if we look at the damage on joint or on damage on beam, dj and db, you can see that if we associate this damage level to the occupancy limit, we don't have damage at the occupancy limit. But if we look at the collapse prevention, you can see that in the joint we can reach 20% of damage in joint as maximum. Also, if we look at the residual load carrying capacity, you can see that in the occupancy level we don't have any reduction of load carrying capacity in all the frames. But if we look at the collapse prevention, you can see, depending on the frame, a very big reduction. We reach like 0.5, more 0.6. So this procedure is not a new procedure because it's based on the EDA, so on a well-known procedure, but can give us very important information on the intervention strategy, because we can relate the EDA with the damage in elements, so we can know what is the damage behavior and where are the damages in all of our elements. And we know what is the residual lead carrying capacity after the earthquake. So maybe we can understand if that frame after the earthquake is safe or not. And of course, we can also evaluate the residual drift, which can be evaluated numerically, like here, or with by the use of the equation of FEMA. The only problem with the low cycle fatigue theory is that for the calibration and for the use of the low cycle fatigue theory, we need to calibrate the curve of the minor of the domain, and we need experimental test. So the experimental test of element and joint for the fatigue is quite limited, so we don't have a lot of tests in literature. But we can overpass this limit by using numerical simulation, for example. Thank you for your